Hello everyone, and welcome to this Chemistry World webinar. I'm Mariana Kneppers, Chemistry World Science Media Producer, and I'll be your guide through the webinar platform we're using today to help you make the most of the next hour. Now to introduce today's speakers. Today's webinar, we will be discussing the ever-growing field of women's health. We're delighted to have two leading experts joining us for this next hour. First, we will hear from Bronwyn Graham. Bronwyn is quite global. She holds positions in both the UK and Australia. Here in the UK, she's the Director of Science, or the Director for the Centre of Sex and Gender Equity in the Health and Medicine at the George Institute for Global Health. Quite a mouthful. Currently, she is based in Sydney at the School of Psychology at UNSW. She works on the cusp of both clinical and academia, blending psychology and neuroscience, and her research focuses on how the female brain regulates emotions with the goal of improving women's mental health. Bronwyn's section has been pre-recorded due to the fact that it is approximately midnight in Australia. So yeah, that's probably the best thing that we can get at the moment. After Bronwyn, we will be hearing from Francesca Duncan, coming to us from Chicago in the US. Francesca is based at Northwestern University. There she is. She is both the co-director of the Center for Reproductive Sciences and an associate professor in the Department of Obstetrics and Gynecology. Her lab uses mammalian models to look at the cellular mechanisms of how aging impacts reproductive potential, with the goal of not only improving the fertile span, but also including the lifespan and health span across generations. Finally, we will end the webinar with our typical Q&A session with all of our panelists, minus Bronwyn. We will be forwarding any questions that you do have for Bronwyn after the webinar's conclusion via email. So please do be sure to submit your questions as they come throughout the course of the webinar. And without further ado, we will start with showing Bronwyn's presentation, which I think Chris will be able to bring up onto the screen here. There we go. All right, enjoy everyone.
Hi everyone, my name is Professor Bronwyn Graham. I'm from the School of Psychology at UNSW and I'm the Director of the Centre for Sex and Gender Equity in Health and Medicine at the George Institute for Global Health. Women experience a greater burden of almost all mental health conditions relative to men, and this is particularly pronounced for anxiety disorders, where women are twice as likely to be diagnosed with anxiety relative to men. So why is this the case? Well, of course, there's a whole range of sociocultural and gender-related factors that may contribute to this. We can't discount the fact that these may be real differences, or they may be differences that are driven by differences in reporting rates. For instance, men may underreport experiencing anxiety symptoms. Of course, there's a whole range of environmental and sociocultural inequities that could account for greater anxiety burden amongst women. And women also do engage in different coping responses to stress that could be driven by early learning experiences. So women engage in greater levels of worry and rumination, as well as avoidance, all of which are risk factors for anxiety. But what I want to talk about in this webinar are sex-based considerations. And as with gender, there's a whole range of different factors that may be at play here. In addition to experiencing greater burden of psychiatric conditions, women also experience greater burden of non-psychiatric conditions across the lifespan. So while women live longer than men, they actually live longer unwell than men. And this is compounded by the fact that many sex-specific medical conditions like endometriosis are underdiagnosed and underrecognized by medical practitioners. For instance, the average time to diagnosis for endometriosis is 7 years. So if women are living with a greater burden of non-psychiatric medical conditions, as well as undiagnosed conditions, it's really hard to have good mental health. Another factor to consider are differences in sleep. Women routinely report experiencing poorer quality sleep, again, across the lifespan relative to men. And sleep is the bedrock of good mental health. So all of these different factors could be contributing to an increased burden of anxiety in women. But what I want to talk about in this webinar are the differences in hormonal profiles between men and women, and in particular, the hormonal exposure that women experience across the lifespan. And so one of the key hormonal exposures that women experience is, of course, the menstrual cycle, which is a monthly fluctuation in sex hormones, including estradiol, which is the main estrogen, and progesterone. And while many people are familiar that many menstruating people experience emotional symptoms and physical symptoms across the cycle, with up to 90% of people reporting experiencing premenstrual syndrome, what people are less aware of is that the menstrual cycle actually impacts all kinds of mental health and neurological conditions, including schizophrenia, depression, even ADHD. And this is also the case with anxiety disorders. So what you're seeing here is data from different studies that has looked at how symptom severity of a range of anxiety disorders fluctuates across the menstrual cycle. So this includes conditions like panic disorder, generalized anxiety disorder, PTSD, social anxiety disorder, and obsessive compulsive disorder. And what you can see is that the symptom severity worsens, indicated by the red shading, during times when sex hormones are high but declining, and then into the menstrual week where sex hormones are at their basal levels, whereas symptoms tend to improve during the mid-cycle, which is when sex hormones are elevated. Now, this impact of the menstrual cycle, while it's robust and it's demonstrated across different anxiety disorders, is by no means experienced by every woman with an anxiety disorder. We know that it's a subgroup of people who experience these effects of the menstrual cycle on their anxiety, but we don't actually know who these women are and what places them at this risk. There's more work to be done. Now, not every woman has a menstrual cycle, and there's lots of reasons for this, but one of the big reasons is the use of hormonal contraceptives, which are used by around 80% of women at some point in their lives. And while hormonal contraceptives have been around for many, many decades, it's only recently that we've thought to ask, what do they do to the brain? We know what hormonal contraceptives do to the ovaries. They expose women to high levels of synthetic hormones, and this stops the ovarian production of estradiol and progesterone. But what does that mean for the brain? So lots of studies have now demonstrated that hormonal contraceptives have an impact on the structure of the brain as well as the function of the brain. And this particular study looked at a type of function called functional connectivity, which is basically how well different regions of the brain are communicating together, how tightly coupled is the activity in these brain regions. And we know that having strong functional connectivity between cortical areas of the brain and limbic regions of the brain, like the amygdala, is indicative of good mental health. Now, what this particular study found is that hormonal contraceptives were associated with a weakening of the functional connectivity between the cortex and the amygdala. And that was exacerbated further the longer that the person had been on the hormonal contraceptive. Now, this is not to say that everybody should throw out their pill packets, because, of course, we know that not everybody who takes a hormonal contraceptive experiences poor mental health. And the large-scale studies that have looked at this have produced inconsistent results, with some studies showing that there's a slight increase in the risk for depression with hormonal contraceptive use, and other studies finding no effects. What is more likely is that, much like the effects of the menstrual cycle on anxiety, the effects of hormonal contraceptives on mental health are going to be subject to large individual differences. So there'll be some women who are sensitive to the effects of hormonal contraceptives and others who are not sensitive to these at all. But again, we currently have no means of identifying who these women are who might be sensitive and how we can predict who is going to be sensitive. Now, the final example of hormone exposure in women across the lifespan that I want to give is pregnancy. So, of course, pregnancy involves a huge hit of hormones to the brain and the body. In fact, the cumulative exposure to these hormones across pregnancy is greater than the cumulative exposure to these hormones across the rest of the non-pregnant life. So it's an absolutely huge exposure to sex hormones during pregnancy. And these sex hormones do impact the brain. So we know now, with research conducted over the past 10 years, that during pregnancy there are grey matter volume reductions in the brain. And rather than being considered a dysfunction, these grey matter reductions are thought to indicate a specialisation of brain function. They're helping the mother prepare to become a parent and to become attuned to her infant. Now, these grey matter reductions are small but highly, highly robust and replicable across different studies. And what's quite amazing about these differences is that they're of identical magnitude to the changes that we see to the adolescent brain across that very important period of development. Now, we know that adolescence is a period of development that is associated with a lot of growth, but is also associated with a lot of risk and vulnerability to mental health conditions. And so too is the peripartum period in women. So we need to take pregnancy into account when we're considering the increased burden of anxiety in women. Now, with all of these different impacts of female-specific factors on mental health, you might be thinking that scientists should be absolutely scrambling to study females, and that particularly given the increased burden of anxiety in females, that most scientists would be including females in their work when they're studying anxiety. But unfortunately, this is not the case. So this is showing the inclusion of females in basic research. So that's preclinical research in rodents and work looking at brain function in humans, conducted in areas relevant to anxiety disorders up until the year 2012. And you can see that of all of the research conducted in these domains up until 2012, less than 2% of it focused on the female brain. Fast forward a decade, and we looked at all of the preclinical research that has studied fear, stress, or anxiety in the year 2021. And we found that still 2/3 of that work was only conducted in males. Now, while this may seem surprising, it's not actually that surprising, because it is reflective of a greater bias in biomedical research, where we know that scientists in general prefer to study what they consider to be a simple male model. But what is a little bit surprising about the fact that this hasn't changed over the past decade is that we now have policies across different regions and countries, including Canada and North America and Europe, that actually require scientists to take sex and gender into account when they are conducting their work. So why is it the case that even though we have these policies, we're still seeing an underrepresentation of females in research and in anxiety research in particular? Well, it comes down to an assumption that many people have, which is that aside from reproduction, females aren't all that different from males. So in my remaining time, what I want to do is present some work that hopefully challenges this notion for all of you. And to do that, I'm going to use the case study of fear extinction. So fear extinction is a really important construct in anxiety disorder research. It is the main mechanism by which we regulate our fear. And ultimately, overcoming anxiety requires the ability to regulate fear. So how do we look at fear extinction in the lab? Well, we use Pavlovian conditioning. And so this is a procedure that can be used in rodents, or it can be used in humans in exactly the same way. We train a subject to associate a neutral cue like a tone or a light with an aversive outcome like a mild shock until they learn that that cue is dangerous. The tone is dangerous, it predicts an aversive outcome. And then the animal starts to show fear responses to that tone alone. And then we can train the animal to reduce its fear responses to that tone by presenting the tone repeatedly without any aversive outcome. And over time, the subject learns that this tone is now safe. And so its fear responses start to reduce. And then we can look at how well the animal has retained that new safety knowledge over time by, again, representing the tone and measuring those fear responses. Now, fear extinction is really important because it forms the basis of exposure therapy for anxiety disorders. So it's the first line treatment for anxiety. With people with anxiety disorders, we do a procedure that mimics fear extinction, where we ask them to engage in approach to feared situations or feared cues in a supportive and a gradual way, such that they learn that the threat is not as big as they thought it would be and that they can cope. So we've studied fear extinction extensively in the lab. We have a really good understanding of the neurobiology of extinction. We know that the amygdala is crucially involved in fear extinction, and we've used that information to improve exposure therapy for humans. But all that work has been done on males. It's only in the last decade that we've started to look at fear extinction in females. So does it matter? Is fear extinction different in females? So we've been looking at the influence of sex hormones and reproductive status on fear extinction. And we've started out looking at that in rats. So we have compared what we call nulliparous rats, so these are virgin rats, to primiparous rats. So these are rats that are mothers. They've had a previous litter of pups. And what we do is put them through a standard fear conditioning and extinction paradigm, exactly like I just described. During extinction training, we group animals according to their menstrual cycle stage. So animals are grouped according to whether they are in proestrus, which for the rat is when they have high levels of sex hormones, or metestrus, which is when they have low levels of sex hormones. And what we want to see is whether their sex hormone levels during extinction influence how well they're able to regulate their fear. And what we see is if you just focus on the nulliparous animals to begin with, if they were extinguished during proestrus, so that's when they have high levels of sex hormones, they show really good extinction. They manage to reduce their fear responses to the cue, and those responses stay low over time. But if they're extinguished during metestrus, which is when they have low levels of sex hormones, they don't extinguish very well. Their fear responses relapse over time. So this is a really robust and replicable effect. It's been replicated across multiple laboratories. But what was novel about this particular study is that when we looked at the primiparous animals, so those are the animals that have had a prior litter of pups, they're our mother rats, they don't show any effect of the menstrual cycle on their extinction at all. They extinguish just fine regardless of whether they have high or low sex hormones. And when we probe that effect further, we actually find that pregnancy causes permanent changes to the cycling of sex hormones over the menstrual cycle. So even though mothers still experience the highs and lows of changes in sex hormones, those changes are blunted. And so that explains why the menstrual cycle doesn't have such a profound impact on their ability to regulate fear. We've also looked at the amygdala to see if the amygdala is involved in fear extinction in females, given that all of this knowledge came from males. And to do this, we inject the animals with a drug called mucimol, which temporarily inactivates the amygdala. during extinction. And then we see how well the animals are able to reduce their fear. And when we do this for the virgin animals, so the non-mothers, what we find is that the animals who had their amygdala inactivated with mucimol, so those are the red animals, they show fear relapse. So just like males, they need the amygdala to inhibit fear. But when we do the exact same procedure to the mums, they extinguish just fine, even without an amygdala. So unlike the virgin female animals and unlike the males, mothers no longer need the amygdala to reduce their fear. We know that they're reducing their fear successfully, we just don't know what brain region they're using to do so. Now, of course, all of that is work in rats, and so you may be wondering, does any of this actually matter for humans? Well, yes, it does. So we have looked at how sex hormones impact exposure therapy, remembering that fear extinction was the model for exposure therapy. And to do this, we had spider-phobic women go through a single session of exposure therapy, and yes, all of them get to the point where they have 2 spiders on their face simultaneously, as I'm modelling for you there. And during this treatment, we measured their levels of estradiol. We had naturally cycling women at different points of the cycle. And we also had women who were taking the pill, so they had chronically suppressed estradiol levels. And then we look 1 week and 3 months later, how successful was treatment? And this is measured really simply just by asking women how close they can get to that spider, with the closest step being reaching your hand into the container and stroking it on the back. And what we find is that while exposure therapy is successful by and large, we find that it is not as successful for women who are taking hormonal contraceptives or those who are in the early follicular phase of their menstrual cycle, which is when sex hormones are low. So remember, fear extinction was more successful when the rats had higher sex hormones. The same is playing out with the humans, where exposure therapy is more successful for those who have higher estradiol levels. And we confirmed this by looking at the estradiol levels measured by a blood test on the day of treatment. And we found that the levels of estradiol that women had during treatment were significantly associated with treatment success across a range of different measures. Now, finally, all of that work was done in women who hadn't had children yet. But what about mothers? So you'll recall that I said that the menstrual cycle has this impact on anxiety symptom severity, but that pregnancy permanently changes the menstrual cycle. So in this particular study, we tracked anxiety and depression symptoms across the menstrual cycle in nulliparous women and parous women. So these are women who've had at least 1 prior pregnancy and birth. And we found that in the nulliparous women, so these are the women who haven't had children before, they show this expected increase in anxiety symptoms and depression symptoms in the early follicular phase, which decrease across the course of the cycle. But in the mothers, we don't see this change at all. And so just like the rats, in the mothers, we're seeing this shift in how sex hormones influence the expression of anxiety. So to conclude, in the domain of anxiety, hopefully I've demonstrated that there are fundamental differences between males and females that are both theoretically but also clinically meaningful. And our assumption that apart from reproduction, females aren't different to males in any meaningful ways has led to the underrepresentation of females in research, and this has really hindered our knowledge of the female unique factors that influence anxiety. What this means is that current evidence-based treatments for anxiety are less evidence-based in females relative to males. But on the flip side, if we only conduct research in males whilst ignoring sex and gender, this also means that we're missing out on identifying the male unique factors that might facilitate knowledge gains and treatment advances in males. So everybody loses through this approach. If we challenge the status quo by including females in biomedical research and account for sex and gender-related factors that might influence outcomes, this creates better and more tailored treatments for everyone, regardless of their sex and gender. So thank you very much to everybody for listening. Thank you very much to everybody who contributed to the work that I presented here in this webinar. And turning over to Francesca now for her talk.
Wow, a big thank you to Bronwyn. That was a fascinating presentation. That spider experiment really, I don't think I would have done well doing that. It gave me anxiety just looking at it. But I found it really interesting, particularly the role that hormones play post-pregnancy and how much that just changes once pregnancy has happened. I just didn't realize how many permanent changes there are. We will now move on, of course, to Francesca's presentation, where she will be focusing on the cellular side of reproductive aging. Francesca?
Well, thank you so much, Mariana, for the introduction, and it's really great to be able to follow Professor Graham's really inspiring talk. I'm really excited to be able to be here today and share our work on ovarian aging to the chemistry world audience, and I'm really grateful that you're featuring women's health, which is such an important topic. So to start with, due to medical and health advances, really globally, our lifespan is increasing. And you can see this really across all continents of our world. But at the same time that our lifespan is increasing, we know that with age, a really key feature of aging is that tissue function really across all organ systems begins to deteriorate with age. That's a key feature of aging. And aging, in fact, because of this deterioration in tissue function, is really the primary risk factor for chronic disease. And so this is data from the United States, which shows that at least 80% of individuals have at least one chronic condition, and about 68% have two or more chronic conditions in adults over the age of 65. And so when we think about lifespan and longevity, it's really not just about living longer, because our lifespan is really composed of two parts. There's a period of life where we're in a healthy state known as health span, but then there's also a period of life where we live in poor quality health, and this is the morbidity period. So when we think about longevity, it's not just about living longer, but living longer healthier. And this means that we need to extend our health span and compress the period of time in this morbid state. So if we think about how we do this, really extending health span requires that we shift the curves or the trajectory of aging in our tissues. And this becomes especially challenging when we think about the female reproductive system, because the female reproductive system is really one of the first to show overt signs of aging in the human body. So when we normally think about aging in tissues, we think about this happening in individuals in their 60s, 70s, and 80s. But what you can see in this graph is that female fertility will begin to decline in women in their mid-30s, and reproductive function will cease completely at the time of menopause, which is around age 50 years old. And really critical to reproductive aging and reproductive longevity is the ovary. This is the organ that houses the eggs, and these eggs are going to develop from a very immature stage to a large stage that can respond to hormonal cues and release an egg every ovulatory cycle that, if sperm are present and fertilization takes place, can give rise to live offspring. And so we typically think about ovarian function as being important for fertility, but also these follicles, as they grow, they produce estrogen and hormones like progesterone, which are really important for endocrine function and endocrine cycles, which we'll come back to. So the female reproductive aging, as I said, the system is really aging before other organ systems in the body. And in the ovary, this reproductive aging is really characterized by two main events. First, there's a decline in the number of eggs in the ovary. So what you can see in this graph and in this image, this movie, and the schematic here is that women are born with a fixed number of follicles. They're not going to make any more eggs than the ones that they have when they're born. And these eggs undergo a continuous loss throughout the reproductive lifespan of the individual, which you can see again in this animation in this graph. And at the same time that you're losing the number of eggs in the ovary, their quality also decreases. And you can see that in the graph in the blue line as an increased fraction of poor quality oocytes with age. And a physician in our field once said that the ovaries are probably the only organs whose peak potential is reached long before their first use, which for me is such a sobering concept. So this reproductive aging has significant clinical ramifications because we know that this loss in egg number and the quality can lead to adverse outcomes like infertility, spontaneous abortion, and in women of advanced reproductive age who are able to conceive, they're at higher risk of dizygotic twinning, obstetrical complications, as well as having offspring with birth defects. And this is becoming more of an issue from a societal perspective because we know that women really across the globe are delaying childbearing. And you can see this in data from the US in this graph that shows the age of first-time motherhood is increasing, is happening more frequently in older women. But it's not just about fertility, as I alluded to before, because we know that these follicles, as they grow, produce hormones like estrogen and progesterone, as well as other hormones that are important for regulating the downstream functions of other organ systems. And so with age, there's a loss of estrogen and progesterone due to loss of follicles, and this can have impacts on other organ systems, so has implications for cardiovascular health, cognitive function, bone health, immune function, sexual function, and so forth. And so I think it's really important to note that while menopause is not a disease, it's part of our normal aging and normal physiology, we as humans have really changed the landscape in which we live. So what this graph shows is that the age of menopause has stayed relatively constant over the past centuries, around 51 years of age. But again, as we saw in that first chart, due to medical and health advances, our life expectancy is increasing quite dramatically. So in the US, the average lifespan for women is around 80. So this means that women are living about 3 decades post-menopause in an altered endocrine environment and potentially experiencing negative health consequences because of it. And I think there is a misconception because females tend to live longer, so they have a longer lifespan than males. So there's a misconception that because they live longer, that they're actually healthier than men. However, that's not true. And you can see this in this graph where there's this female-male morbidity mortality paradox where women are actually spending more of their later years in poor quality health and frailty relative to men. And this can be in part due to the fact that they're living much longer in this postmenopausal state. And in fact, we know that there is a relationship between age of menopause and life expectancy, with women who go through menopause later in life having a longer life expectancy. And so when I think about the area of health span and lifespan and longevity, I think we need to reframe our research on aging and longevity. So it's not about lifespan, as I mentioned, it's about health span. But when we're dealing with women, we have to encompass the reproductive span within that concept of health span for women. And so this has really motivated the work and the research that I do in my lab every day, which I'll spend the next part of the talk telling you a little bit about. So as I mentioned, the ovary, the key features of aging are a loss in the number of the eggs in the ovary and the quality of the eggs within that ovary. And so not surprisingly, a lot of research in this space is focused on what are the changes that happen in the egg itself with age. And when I started my lab about a decade ago, we actually started to think beyond the egg and thinking about the environment in which the egg develops, and could this perhaps influence ovarian aging? And so what you can see in these two images, these are histological sections of mouse ovaries. On the left side, you can see a young ovary. This is an animal 6 to 12 weeks of age, which would be equivalent to a woman in her 20s. Whereas on the other side, you can see an ovary from a mouse that's 14 to 17 months of age, which we consider reproductively old. This would be equivalent to a woman in her late 30s or early 40s. And the circular structures that you see there are follicles. And so, as I said, with age in humans and in mouse, there's this decrease in the number of these follicles in the ovary as expected. But if you look at all the surrounding tissue where these eggs are developing, I hope even in an untrained eye, you can appreciate that these environments look quite different. And the way we isolate these follicles to study them in the lab is we poke them with needles to dissociate the tissue and remove the follicles. And some undergraduates and technicians who were doing these studies in the lab when we were trying to look at the follicles between young and old mice made this very simple observation that it was just really hard to get those follicles out of the old ovaries compared to the young, where they would just fall out with this mechanical poking. And so this got us thinking about this concept of fibroinflammation, or excessive immune responses and scarring of tissue, which is known to happen in other tissues with age, like in the heart, lung, and kidney. And it's associated with tissue damage and homeostatic dysregulation. And this leads to sort of the toughening of that tissue. And so while this is associated and common in aging tissues, remember the ovary is aging much earlier relative to these other organ systems. And so this set us on a trajectory to start shifting away from the egg and looking at what's happening to the environment. And so we asked a simple question: is there evidence of inflammation and fibrosis within the ovary? And what you can see here on the top graphs, this shows that there is production of high levels of pro-inflammatory molecules, both at the transcript level and what's secreted by the ovary, and this is with IL-6. You can see that this increases significantly with age. We also can see in those top images that there are a group of specialized immune cells called multinucleated macrophage giant cells that are highly penetrant in old ovaries, and they're never found in young ovaries. And these are typically associated with tissues where there's high levels of chronic inflammation. Now, inflammation typically comes before a fibrotic response. And so because we saw inflammation and we knew that these tissues seemed tougher, we wanted to actually confirm that there was fibrosis present. And so we can stain for fibrotic tissue with collagen 1 and 3 stain, when this red stain called picroserous red. And on the bottom there, you can see that there are fibrotic foci that form within the ovary and expand quite dramatically with age. And these changes that we see in the mouse are also conserved in the human ovary. And so you can see on the left in these graphs, these are a series of fibroinflammatory cytokines that increase significantly in follicular fluid in women with age. And we can also see on the images of the tissue from an ovarian tissue microarray, we looked at tissues from 60 individuals ranging in age from half a year to about 58 years of age. And we can see here in the quantification of the collagen that fibrosis also increases in the human with age. So we then went on to see what is the consequence of this fibrotic tissue. Again, we had a sense that this was leading to a toughening of the tissue because it was harder to get the follicles out. But to get a biomechanical measure of this, we performed instrumental indentation, which is a technique in which you take a probe and you're measuring the amount of force it takes to indent a tissue a given distance. So the more force that it takes, this is a readout of a more stiff tissue. And in fact, what you can see in that middle graph is that if you do this in old ovaries compared to young ovaries, it takes more force to push on that tissue, demonstrating that there is a quantifiable increase in ovarian stiffness. Now, I don't have time to go into the biological consequences, all the primary data that led to this, but this actually matters. So if you have a stiffer ovary, this leads to the impaired ability of these follicles to grow in the ovary and function. It causes a reduction in the quality of the eggs that are produced in a stiffer environment, and it can actually block the ovulatory process from happening. And it also has important implications for disease. So ovarian cancer is typically diagnosed in postmenopausal women, and ovarian cancer cells prefer to be honing in on a stiff, rigid, collagen-rich matrix, of which the aging ovary is one. And so this work all together really started shifting the perspective in our field of ovarian aging, that it's not just about the egg and undergoing changes within the egg itself, but also changes in that nest or that environment of the egg that ultimately leads to adverse outcomes in ovarian function. And so now our work is really focused on taking what we've learned in the laboratory and translating it into the clinic, which I will share in the last part of my talk, in how we're actually trying to modulate ovarian stiffness to soften the ovary and keep it it in a young state, how we're trying to model this environment so we can actually use it for drug discovery approaches, and then also how we're translating this into a biomarker. So again, because of these biological consequences of the stiffness of the ovary, we asked, can we actually modulate this parameter? So we treated old ovaries with collagenase, which is an enzyme that digests collagen, which we know is enriched in the old ovary. And you can see in these images that we can, with this collagenase treatment, restore the collagen content of the old ovary so it looks like a young ovary. And when we repeat our biomechanical assay, we can see that with the collagenase treatment in the graph, we can now restore the biomechanical properties of the old ovary so it looks much more similar to a young ovary. So this gave us proof of concept that this parameter is able to be modulated. And so we wondered, could we actually in a preclinical study show proof of concept that if we used an anti-fibrotic drug that we could prevent fibrosis from happening and actually maintain a healthy ovary. And so I won't be able to go into all of the details. This is a published study, so if you're interested, I urge you to look at the details of that study. But the idea here is that we started treating with mice at 7 months of age when fibrosis starts with an FDA-approved anti-fibrotic drug for a period of 6 weeks, and then we removed the drug and allowed the animals to age out 3 additional months where we looked at what the outcome was on the ovary. And what you can see in the pictures on this slide is that in our animals treated with the anti-fibrotic drug, there's significantly less fibrotic tissue within the ovaries treated with this drug. And what you'll see in the architecture of the ovary is that there are many more follicles, so those circular structures within the mice that are treated with the anti-fibrotic relative to the control, and also those circular structures that are lighter pink color, those are actually remnants of ovulation. So in this study, we were able to show that this drug can actually prevent fibrosis and inflammation and extend hormone production and follicular development within this model. And so this really shows clinical proof of concept in a preclinical model that this could have significant implications for reproductive function and longevity. But the problem with this study is that while this drug is FDA approved, it's approved for idiopathic pulmonary fibrosis in individuals who are quite sick, and it does have liver toxicity side effects. So this drug could never be used in a clinical setting for this purpose. And so right now we're really focused on identifying molecules that are specifically targetable for ovarian fibrosis. And to do this, we've developed a novel model that allows us to study the environment of the follicles and the eggs in isolation. And so we've developed an organoid model, which I'm showing you here, where we're really culturing all of the somatic cells of the ovary without the contribution of the germ cell. And so we're really looking at how the microenvironment of the ovary changes. And so what you can see in these images is that we can do this in both the mouse and the non-human primate, which gives us great confidence that we can also move this forward in the human. But what you can see there from that UMAP, which is single cell data, is that we're able to really preserve and culture all of the different heterogeneous cell types that are present in that ovarian environment. And what's really exciting about this organoid model is that if we culture these organoids for a period of about 3 weeks, they actually exhibit fibrosis in a dish, which you can see with that collagen staining there at the bottom. And so this enables a really exciting tool where we can look at drugs that actually prevent this fibrosis from happening, but also when fibrosis has already been established, we can screen for drugs that actually reverse this fibrotic response. And so we think that this model will really help us push forward drug discovery to find molecules that are specific to ovarian fibrosis. Now, finally, as we push towards clinical translation in terms of developing therapeutics to target the stiffness of the ovary, we have to have a real-time ability to measure whether or not these drug treatments are actually efficacious. And we also think that the ovarian stiffness can be an important biomarker of ovarian function. So we've now been using technology known as shear wave elastography, which has been used clinically to measure fibrosis in other conditions, for example, in liver fibrosis. This is an ultrasound-based method where the principle is that you propagate an ultrasound wave through a tissue. If it's a soft tissue, these waves will propagate more slowly, and in a stiff tissue, these waves will propagate more rapidly. And this can be then translated by an algorithm into a specific stiffness measurement. And so we're able to measure the stiffness of the human ovary in a minimally invasive way through transvaginal ultrasonography. You can see on the top image there that that's a ultrasound image of an ovary. The black spaces are follicular structures, and the S is denoting the stroma where we're actually making these measurements. And with this technology, we can make measurements of, we have an image for each measurement we make of a confidence map, which shows us that we're making measurements in high confidence regions. For example, excluding regions where there's fluid, which would give us an artifact reading. So we're only really making measurements in high confidence regions. And then in those particular regions, we can then measure the specific stiffness of that particular spot. And so in that montage of images there, what you're seeing are 12 measurements made from one individual ovary. We make multiple measurements that overlaps to get a really good coverage of the ovary. And so what we can see here is that we actually, not showing this data, but we've shown that age is actually not associated with the mean stiffness of the ovary, which is very similar to what we see in the mouse, where it's not the entire ovary that becomes stiff, but actually really specific fibrotic foci that begin to form. And so just like that in the human, we don't see changes in overall stiffness, but what we see are really significant changes in the heterogeneity of the stiffness of the ovary. So elastic heterogeneity is essentially the average of the 3 highest stiffness measurements subtracted from the average of the 3 lowest stiffness measurements in the ovary. So we can see that in that top graph, there is a significant increase in how heterogeneous the ovary becomes with respect to its stiffness, and also that there are these specific regions of fibrotic regions within the ovary, and that's shown here as a significant association of age with maximum stiffness measurements in individual ovaries. And we know that for other examples, like in the cancer field, maximum stiffness can be prognostic in terms of aggressiveness of various cancers. And so this is really interesting, and it shows us that our work in the mouse is translated into the human, but also that we can measure this parameter in real time. So in conclusion, I hope I have convinced you that I think ovarian aging is really holding some of the keys to healthy longevity in women. And then specifically in our work with ovarian aging, ovarian inflammation, fibrosis, and stiffness increase with age. This has implications for the physiology of the ovary with respect to follicular development, egg quality, and ovulation, but also could have important ramifications for pathologies like ovarian cancer. We think that the stiffness of that ovary, that fibrosis, represents a therapeutic target where we can soften the ovary and keep it in a more young state to be able to modulate the reproductive longevity of an individual. And we think that tools like the ovarian somatic organoids really allows us to study this particular compartment or the nest of the ovary, and will accelerate the identification of new drug targets, whether they be antifibrotics or other that are focused not on the egg itself, but on that nest environment. And being able to measure this parameter itself could be a biomarker of ovarian function, which we're currently looking at, but also will allow us to enable the efficacy and safety of emerging therapeutics. And I think about this challenge, and I think as a society, we've all accepted the challenge that we want to live longer. That's again evidenced in the fact that we are living longer and taking medical interventions and health and lifestyle interventions to be able to live longer. But for women, our biological clocks really haven't aligned. And so I think really the goal here is to reset and realign these biological clocks so we can ensure healthy aging in women, which we need to remember really half the world's population and who are absolutely essential for the continuity of our species. So with that, I will end my talk and stop sharing and take any questions if there's time. Oh, and actually, whoops. I forgot to acknowledge all of the wonderful people in my lab. I have that slide. There we go. Thank you so much for putting that up there, because these are the most important individuals who over the period of a decade have done this incredible work. And also this is very collaborative work. I couldn't have done this at all without many, many collaborators and a rich source of funding. And so I thank everyone for that, and the audience for all of these wonderful emojis.
Yeah, they've just been flooding in, honestly. I mean, thank you so much, first of all, for that presentation. I mean, it always astonishes me how many topics within women's health are fundamentally new to me. And it happens so often. And I don't know if that's a testament to either my ignorance or the fact that we're still learning so much about female biology. And it's all just so necessary and really exciting. So yeah, thank you so much for that, and to Bronwyn, who's not here, but for fantastic presentations. We do have some time for questions, and we have some great questions that have come in, and I have some myself that I would love to ask you. But let's go ahead and start with this one, which is, why does the ovary age earlier than other tissues in the body?
That is a wonderful question, and something that I have thought quite a bit about, and I do get this question quite a bit. And I think it has to do with the demands of this organ that I don't think people always realize. And so, women are born with millions of follicles, but only about 400 will ovulate. And so what happens to the rest of those million of follicles? Well, they undergo a death process. And you can imagine that all of that debris that happens from these dying follicles, that starts happening when, females are born, this waves of death, this has to be managed. Now, we also have ovulation that's happening, right? That's a wound, that's a rupture and a wound that's happening every month in women. And so this organ has to wound and heal repetitively over time. And then also there's a structure after ovulation called the corpus luteum. This is the remnant of the follicle, and this produces hormones that could support pregnancy. But if pregnancy is not happening, that structure has to basically deteriorate. So you have an extremely dynamic organ that has a very high demand of debris. And we know that debris and aging is really important. So if you think about neurodegenerative diseases, there's lots of stuff that accumulates, debris that accumulates in the brain, and that's what's causing the neurodegeneration and that aspect. I think something similar is happening in the ovary, where you have this excessive amount of debris over time, and the ovary can't keep up with it, and this sets off this cascade of inflammation and fibrosis that kind of feeds forward.
Yeah, I mean, when you think about it, even looking at that graph you had in the beginning of the presentation, you see how soon that kind of the health of the ovaries just kind of dips. And it's just, there's so much hormone production, follicular growth, all of these things are happening. That organ is going through so much change. Something that I don't think any other organs really go through that same degree of change. So that does make sense when you put it that way.
Yeah.
Yeah. Does that have anything to do with kind of the mitochondrial dysfunction? Because I know in a lot of aging studies nowadays, they are focusing on, the deterioration of the mitochondria. Anybody in grade school knows the mitochondria is the powerhouse of the cell.
Yes.
How does that kind of feed in at all?
Yes, absolutely. So I think it's very well established that there's mitochondrial dysfunction that happens with age within the egg itself. And that really changes the quality of the eggs with age. And so, are there ways to boost the energy production or the function of mitochondria with age directly in the egg to improve egg quality? That's one aspect. But there's also more recent data where people are starting to look more at what's happening in, again, the somatic compartment of the ovary, and showing that there's mitochondrial dysfunction, not just in the egg, but also in those nest cells, and ways to prevent reactive oxygen species, to boost mitochondrial function, are all really important strategies to improve ovarian aging. So absolutely, you are right on target there.
I'm glad my high school biology teacher would be really proud of me right now. Another question for you. This comes from Wayne in the UK. And they ask, how can non-specialists such as science technicians or educators help support awareness of women's health inequalities?
That is a wonderful question. I mean, I think in particular in this time, right now, like there's a lot more awareness of this particular topic because it has such tangible clinical and societal ramifications. So both from the fertility angle, because women are delaying childbearing and families are experiencing changes to sort of their family planning goals because of this, but also, again, because women are living longer and we're much more aware. And so I think there is again, more societal awareness where we have webinars like this, where you see more articles in the public, sphere talking about this. And I think it is really having those conversations, increasing awareness on this, that is really, we all have a part in this. And that we're focused on women's health here because it does age so much earlier than other organ systems, but men also undergo reproductive aging. And that's a sort of a much newer area relative to the female side, because again, men can sire children much, much later. So there was always this assumption that there isn't an age effect, but we are now starting to understand that it's much more complicated. So I think awareness of the importance of this topic of fertility and beyond fertility, it's not just about fertility, it's about overall health, and that's going to impact our whole population, but also that the conversation isn't just about women, that we have to start thinking about, we're an aging population. These experiments are being done in biology right now, like older parents, they're older fathers and mothers. And so what are the consequences? And so I think just being a lot more open and understanding and spreading the word would be extremely helpful.
Yeah, it is that thing of, it's not a one size fits all solution. And that, like you say, it applies not only to women, but men as well. And there's kind of the lesser known, concept of the menopause, which is like the men's version of menopause. And it does exist. So it is, I agree, you do have to talk about both sides. It's that kind of not one size fits all. It is very, how do we tailor this? It's all really interesting. I had a question for you from something in your presentation that you had mentioned. I don't know if it was on a graph or what it was, but one of the kind of side effects of an aging ovary is that you have a higher rate of dizygotic pregnancies, so like twins essentially. Mm-hmm. Why does that happen? As you get older, is it safe to say, first of all, as you get older, there's a higher likelihood of having twins?
Yes, and that's independent of the use of assisted reproduction. So obviously, like twinning could increase because women of advanced reproductive age are relying on assisted reproduction. So for example, they might have more than one embryo transferred, in which case, if they're doing IVF, in which case, obviously you're at a higher risk of twinning. So you can see it that way, because again, like there you have an increase, and most countries are moving towards single embryo transfer. So the number of twinning and multiple pregnancies is reduced because, again, there's concerns about there's risks of multiple pregnancies. So you see a higher risk of multiple pregnancies in age because of that reliance on assisted reproduction. But even in the absence of assisted reproduction, aging is associated with a higher incidence of twinning, which I think just kind of talks about with the fact that with aging, there's sort of dysregulation of various processes so that you end up with situations like a higher incidence of twinning. Does that make sense? So it's both. It's both because of a higher use of assisted reproduction, but also because of biology.
I see. Okay. And does that have to do with the kind of, you have these ovaries that are less flexible, so it's just extra complications, isn't it? So things like that can happen, or?
So we haven't, it's really difficult to study that, for example, like the cause and effect of stiffening of a tissue on like the twinning process in the mouse, because they're polyovulatory, so it's hard to figure that out. We do know that the stiffness of a tissue can impact ovulation. It usually actually prevents ovulation. It's it's harder to rupture out of the ovary. So I don't think that there's a issue with twinning because of that, but certainly there could just be broader dysregulation from the endocrine axis and the function of the ovary.
I see. Okay, that makes sense. We'll do one more question. I know we're just at the end, but I always love asking this question. What is next for your research?
Yeah, so as I hope I tried to convince you, I mean, I spent the first half of my career trying to understand the phenomenon of what's happening in the ovary with age and looking at the mechanisms. And now we're really trying to get into the clinic and developing these biomarkers and therapeutics. But another thing that I'm super interested, I think the areas that I'm most excited about are how is the ovary communicating to the rest of the body when it starts off this aging process so early? Is that sending signals to other organs to start the aging process? And I also am super, I guess, as it's tracking with my own with my own age, I'm really interested in the menopausal ovary and perimenopausal ovary, and really trying to understand, is it truly just sitting there as a defunct organ, or is it actually still doing something, and what is it doing, and is it a good thing or a bad thing?
Yeah, wow. All really, really important questions. And we're really excited to see, just kind of keep in tune with your research and see what comes next. It's all very exciting stuff.
Well, thank you so much.
Yeah, of course. So that leads me to my thank yous. Thank you to both yourself, Francesca, and Bronwyn for dedicating their time for this fascinating and eye-opening presentation. I'd also like to thank my wonderful Chemistry World digital team. We have Chris Pink and Ben Vassler, who have been working behind the scenes to make us all sound and look pretty, and making sure everything runs smoothly. This webinar was born out of the Women's Health issue of the Chemistry World magazine. If you would like to learn more about this topic or other topics related to women's health, we will include a link to the Women's Health online collection in the webinar follow-up emails. Thank you all for joining us. We hope to see you in another Chemistry World webinar soon. I'm Mariana Kneppers, Chemistry World Science Media Producer. Goodbye and see you next time.